In this video, we are going to work upon multi-class segmentation using the PyTorch framework. So let's take a look at the dataset first. Here we are using Weeds dataset, and this dataset contain near about 708 images and their respective RGB mask. So here you can see a few images, and these all images are resized to 512 by 512, which is good for us. So because now we don't need to think about the proper sizing, that is already done for us. And if we closely observe that these are basically cropped from a larger image, that is also good. And now their respective mask. So this mask contain two main class, basically two kinds of weed. First is in red and second was in green. Yeah, green one. And the third main class is the background. So we have 2 plus 1 main class. Two are the weeds and the third one is the background. Now the dataset part is done. We'll move on to the code. So here first of all we'll have our unit architecture, and it is about 10 years for this architecture to exist. I hope everybody knows about it. If you don't know about it, let me explain it in a simple term. So it has two main part. First is the encoder, which takes your image and process it, and each encoder block is built using these convolutional block and a max pool layer. So this convolutional block itself contains two conv layer. It has convolution layer, batch normalization, ReLU activation function. Again we repeat same set of layer. So this is the encoder, and then we have the decoder. So what decoder does is it expands the feature map, and at the end generate the segmentation mask. So this decoder basically starts with a transpose convolution, upsampling the feature map by factor of 2, and then it is followed by the conv block. So this is how it works, and in between encoder and the decoder we have a simple conv block, and at last we have our output layer. And in this layer we have the num classes, that is how many class we have. We have 2 plus 1 class as the number of output channel. So this is about this unit architecture. I have few videos explaining the things about this unit architecture. You can watch those videos. So this is done. Now let's move on to the utils file. So this is these are few functions which are important for us. So I'll explain you each of them step by step, because I'll write them. It would take a lot of time, and this video would become a hour-long video. So first our function is seeding. This function makes sure that we seed the randomness. This makes sure the random number which are generated are same during training and testing. We just want to make sure that the randomness is saved every time, so that the results are reproducible. They do not change because of the randomness, because we are working with deep neural network, and they have various things which require random numbers. Like your weight, they are randomly initialized, but when you seed, their randomness would be same every time. That is why we seed our environment in both training and testing with the same seed number. Next we have a function called create dir. So what this function does, it check if a folder exists or not, and if it does not exist, it create that folder. So it's a simple function. Next we have a function called shuffling. So it simply take two list and shuffle those like its name. Next we have a function called epoch time. So this epoch time basically calculate how many minute and second are there between the start time and the end time. This is used between epochs, like before the start of the epoch and when the epoch ends. So how much time a single epoch take, this is where it is used. Next we have a function called load checkpoint. During training we save our checkpoint. So, and maybe during testing or some other, maybe during training also, we want to load a checkpoint, a specific checkpoint. So this is where this function come. So it take model, then optimizer, and the checkpoint path. So first of all we check if the checkpoint exists. If it exists, we do something, and if that checkpoint does not exist, we simply say no checkpoint exists. So we give simply back the model optimizer and 0 as the initial epoch. So if that checkpoint exists, we load it, and inside we have the model weights, then we have optimizer weights, then we have the epoch, at what epoch this weight file is saved, and then we say the checkpoint is loaded from this specific epoch, and then we give back our model with the weights and the optimizer and epoch. So this is that. And next function is save checkpoint. So in this function we basically save the epoch, on what epoch we are saving our model or the checkpoint. Then we save our model weights, then we save our optimizer weights, and then we have the loss function for that specific epoch. We save. Next we have early stopping class. So this is just to check that after these much amount of epoch, if there is no improvement, so the training should stop. And if the loss improves, means if the values decrease, it should save the checkpoint. So these are our few functions. Next we have losses. So we have this dice loss, then we have a combination of dice plus cross entropy. So in this video we are going to use this dice plus cross entropy as our main loss function. So these are all about the code. Now we'll move on to the training part, which is really important because that is the main part which we need to focus on. So now we'll one by one we'll write all the code. So first of all we'll import all the library functionality which we require. So you can see we have OS, random, time, date time, and all these functions. We're going to use them one by one. So now we start with our main function, and I hate these autocomplete. So if you guys have any other text editor which don't provide this autocomplete, please recommend it to me, because I don't like these autocomplete. Now let me do one thing. Let me start with our main. So here's our main statement, and this is from where the execution of the model start, the file start. So first of all we are feeding the environment. Next we have our if folder in which we are going to save our weight file and other files which we need. Then we have our hyper parameters. So we are going to resize the image to 256 by 256. Then we have our batch size as 16. So this batch size need to be according to your requirement, because I have a 3090 which has 24 GB memory, so it can accommodate batch size 16 with a specific size and the parameter I have. So you can decrease it or increase it according to your GPU. Then we have start epoch. It will start with 0. Then we have number of epoch, and I've set it to 500 as the max value because we have early stopping to stop it. Then we have learning rate 1e minus 2. So 1e minus 2 basically refers to 0.01. Then we have early stopping. So how many epoch view if there's if we are training and like for 50 continuous epoch the values does not decrease, so you want to stop it. Next we have the checkpoint path where we want to save our checkpoint, and this is our data set. So we have, for now we have the data set in the same folder, and here are our RGB codes. So we have first the background, then we have this class 1, then class 2. So these are 2 kinds of view, and then we have this number of classes. Now so this all is done. Now next would be our data set. We need to work upon that function. So here's our data set function. So for now I'll simply copy paste this function above, and I'll explain what it does. So what it does simply is we give it the dataset path. So first of all it load all the images and their respective mask. Then we make sure that the length of both the list are same. Then we split the data into training validation, and then test. So we split the data into like 60% of the data is used for training, then next 20% would be used for validation, and next 20% would be used for the testing. So this is how we divide it. Now let's load the data set and print how many images do we have for each of the thing, like for training, validation, and test. So let me run. Okay, first of all we need to activate our environment. So this is our training file. Okay, so you can see we have 4700 images for the training, then 1500 for validation and testing. So this is enough, and the size is also good. Now let's work on the rest of the code. So now we'll define few things. First of all, I'll define the data augmentation. So here's the data augmentation which we're going to use. Next we have one important thing, that is the dataset. So let me simply paste it. So this dataset class is important. So this is the main function which we're going to use to build the training pipeline. Without this function, things are incomplete. So this not the function, is a class. So this class first takes the image path, masks path. So these are basically list, then size of the image, then the RGB code, and then the transform. That is, transform basically represent the augmentation which we're going to perform. Then this is the main function where all the processing happens. Okay, so first of all, what we do, we read all the images. Sorry, not all the images. So in this get item function, we have an index number, and from the list we take individual image and mask. We have their path, we read image and mask as an RGB image only, because now both our images and mask are in RGB. Then if we provide some transform to this, we pass it via this transform, and images and mask are augmented. Then we resize the image, transpose it. We need to transpose it because by default the image is like height, width, and then the number of channel. But in the PyTorch, we need to make sure first we have a channel, then height and width. Then we normalize the image by dividing it with 255. 255 basically maximum pixel value. So it transforms the pixel values in the range of 0 and 1. We do the same operation with mask. We first resize it, then convert it into unsigned integer 8. Yeah. Then this is the process which would help us to transform this RGB mask into an index class mask. So I also have a video on that, how you can convert an RGB mask into index class mask. Code is also there. So let me just simply show you. Mask class, we have initialize an empty and numpy array with all the values 0. So 0 basically define the background. So by default everything is background. Now we need to fill specific values like class number 1 or 2. 1 or 2 indicate weed 1, weed 2. Not that smoking weed unnecessary plant. Yeah, this is class 1, this is class 2. Now we run this upon this list. So we have a specific index and the color. Now first it's going to iterate over the background. So background value is 0. So by default, so now we have this mask. Okay, it matches this specific RGB code in this mask, and on all those places in the mask class it replaces with the specific index number. So first it replaces everything with 0, then with 1, then with 2, and because after 2 we don't have anything, so things are done. So like this we have images and mask. So during training, let me just give you one thing. So how does it take thing? Yeah, autocomplete works this time. So your image should be channel, height and width, and your mask should be height and width, just that. You don't need to provide any specific class like this. or something like this, because we have three class here, so three number of no, it does not work like that. Just need to provide a single layer channel, single channel array, with just values from 0 till your classes, so 0 1 2 in our case. So now this part is done. What we need to do is we need to work upon the dataset and the loader. So we have this transform, then we have our dataset where we provide training images and the validation dataset, and we have two things, train dataset and validation dataset. Then we have these data loader which we use, and now our training pipeline, basically the training dataset pipeline is done. Now we're going to work upon the model. Okay, so first of all, we check whether we have a CUDA device or everything is going to be trained on a CPU. So if you have a NVIDIA GPU and your libraries are properly installed, it would run automatically run on CUDA. If not, if there's any problem, maybe you don't have the GPU, you don't have proper library installed, because CUDA installation is another level headache. I have faced it multiple times. Because of that thing only, I never do unnecessary stuff with the Ubuntu, because once this is done, you need to do everything from scratch. Everything is fine, maybe take days, just that installing those CUDA libraries is super headache, especially for me. Still after all those years, I feel that as a headache. So now after the device, we have our unit. We specify number of classes in it, and then we load the device to our GPU or the CPU. Here also we also print our GPU. This is I have done just to check what devices we have. Then initially I think I've done with this Atom. We are not using Atom W. Then we have SGD optimizer. Then we have this scheduler, reduce alarm on plateau. After that we have early stopping. I already explained it. Now we load the model. If it exists, it's fine, otherwise. So this is for the condition if you have trained it and you have stopped it, so this function would automatically load that. Next we have dice plus cross entropy loss function. Let me remove this. Yeah, so this is all. Now we need to write two functions. First is train and second is evaluate. So these are the two functions which we need to work upon. So I'm going to first explain the train function. So train function is it represent an operation which is going to perform on a single epoch, and we're going to use this function again and again over multiple epochs. Okay, so it take your model, then the dataset loader, then optimizer, loss function, and your device GPU or CPU. So first we make sure our model is in train phase. Then we have an empty variable, say 0.0 representing an epoch loss. Then we have this scalar. We are using AMP here to improve our GPU optimization so that we can increase our batch size and we can train it with a greater batch size. So this is something AMP is kind of different, but I know that it improves your, it decreases your training time and it reduces your memory consumption so that you can have more batch size. Now we iterate over this dataset loader. So we have X as the batch X and batch. So this is a batch of images X and batch of mask Y. So we load them to GPU. Now remember one thing, when you are working with multi-class segmentation in PyTorch, your images is float 32, but your mask would be torch.long only. Just remember that. This is rule. This is important. Remember? This is important. Why should be long for cross entropy? Now autocomplete is working fine. Then we do some calculation, loss function, optimization. Okay. And inside this CUDA AMP. So we give the model images, it do some prediction, then we calculate the loss function, then with this loss function we optimize it, do stuff using back propagation, and at last we calculate the epoch loss, what is the average loss over all these. Same we have during the evaluate, just that here we do not perform the back propagation, here we just calculate the loss on the validation data set. Now everything is done, we can begin with the training. Okay, so this is thing. Now let's start with the training and see there's any error or anything. So you can see GPU device name NVIDIA G4 RTX 3090. So I won't be able to train it much, but I'll show you I think 1 or 2 epoch. Now you can see a message, no checkpoint found starting from scratch. But if there's some weight file saved in this files folder, it would load that. So that is the advantage of that function, this load checkpoint. It helps you to continue training from your last moment where you have left it. Next would be our test file. I hope this training would begin soon, otherwise we're gonna work upon our test file. Okay, let's do one thing. We can work with our test file and leave it here. So first of all, simply we need to load all the libraries, the most important one. Next we have a function which I have taken from my last video, and that function is converting index mask to RGB. So index mask is basically what it is, a mask where we have classes index 0 1 2 3 4. So it convert it into its proper RGB code so that we can easily see it. Now you can see our model is trained with 1 epoch, and each epoch take 1 minute 4 second, and training loss is 1.09, val loss is 1.003, and it's saved the first epoch. Now let it also run for another epoch. Now let me write the next part of the code. So this is our main function from where the execution start. Again we seed the environment, we have our hyperparameters where we have specified the image size, height and width basically. Then we have the RGB code, dataset path, number of classes, name of classes. I basically don't know what each vid is, so I've simply given them the name, background, vid1, vid2. Okay, next epoch is also complete. I need to stop it because it would be wastage of resources, because I've already trained it for few epochs. We can use that weight file. So now you can see it saves, and now I'll run it again to see how this load checkpoint work. You can see checkpoint loaded from epoch 2. So this is how that function is helpful. Now let's stop this and continue with our this. Now here we load our checkpoint, then we have our data set, but we only need the test set. So we create another folder called result, and inside result we have 2 folder, mask and joint. Okay, then we have function called evaluate where we have model, save path, test x, that is images path, mask path, size, RGB code, and the classes, these classes names. So I can simply do is, okay, I can simply paste the entire, not the entire code, it won't be good. Let me just do it step by step. It would be easier to understand even for you and me also. Okay, so this is defining. So we all know what it take. Next we're gonna iterate over the test images and test mask. So we have few things here, time taken, an empty list, score an empty list. Then we iterate over test x and test y. Then we extract the name, don't autocomplete, extract the name from this. So let me show you the name so that you know what it is. Test. So this is the name of the image. We have also removed the extension. Okay. Now we need to work upon the image part. We're going to read the image. Why this stupid thing came? So here we have read the image, resize it, and save the image in another variable. Save image. Then we transpose it, normalize it, expand the dimension. Because now here we are giving single image to model. So we need to create a batch of it, so that's why we extend its dimension. So here, let me just show you. It was like channel height and width, but here, yeah, it became one channel height, and so it's a batch size which only contain one image. Next, we're going to work on the mask processing. So here we read the mask as RGB, we resize it, save it, say copy and save mask. Then we convert it into RGB, not RGB, class index mask. And here we have something, we have some predictions. Now we are going to make a prediction. So for FPS calculation, how many FPS frame per second it does, we have some start time here. Then what we do, we take the image, give it to the model, we have prediction, then we pass it via the softmax. So softmax, what it does, we have our logits, we passes them via softmax. So softmax basically give a probability. Okay, for now we have 3 class. Okay, so it provides softmax probability over each class and which for each pixel. Okay, and whichever class have maximum probability, basically we said this class belong to that specific index. So if on the background we have 80% probability, and let's say we have 10% for class 1 and 10% for class 2, so because 80% is more than 10, so that pixel would be a background. And same thing happen if your class 1 is 80% and rest is 10% or any other value. So whichever class is maximum would automatically be assigned to that. So this entire operation happen over the whole mask. Okay, then we have argmax. So argmax basically select whichever index has the maximum value and assign a value. Then at the end we stop our time and we append it to our empty list time taken. Now what we're going to do, we're going to save our mask. Okay, here what we do, we concatenate all the images into a single image. Save image is line separating, a white line separating image and mask, and then again a line separating prediction and ground truth mask. So we convert the prediction, that is index mask, to RGB, and we also save individual masks. So now what's let me just run this and see if there's any error. Yeah, but we need to train it more now. We need to replace the file. Let's also see how it works. Okay, so see, if you see this with 2 epoch, it's working fine. Okay, this is just 2 epochs, no more, no less. Okay, and in the mask we have individual mask, because when you do research and write paper, so you need those individual masks to paste. That's why I saved them. Now we are done with saving the. We can also work on calculating the score. Okay, I'll do one thing. I like this part, this much part of it. So here what we do, we take ground truth value and the predicted value, we flatten them. Then we have the labels. Basically these are number of classes, so we have 3 class here, so labels would be 0, 1 and 2. Then here we use f1 function and the checkout. So we calculate f1 and the jack value and we append it to our score. Okay, here, so for individual image we have calculated is f1 and checkout. And these are not mean value all class, these are over all the three class. So if you want, I can, these autocomplete is shits sometime. F1 score, I'll show you. Oh, incorrect. It should be F1 value, not F1 score. F1 score is a function. How would it give anything? So you can see we have a list which contains three value. So you can see now this value is over the, so this value, okay. Same we can do with Jack, because we have not replaced it with our train file, so it would give you not good values. So we have these scores. So now what we do, so we come now, all the operations would happen after after the outside the loop, because now let's say our loop is done. So we're gonna print the result or matrix. So here's our score, we convert it into a numpy and we perform a mean over the axis 0. Axis 0 means we perform a mean operation over all the images. Now what we do, we're going to save it in a file also. So let me just paste the entire code here and I'll explain it. Yeah, get rid of the terminal. So we have this file called score.csv, and inside we have class, name of the class, there will be background v1 v2. Then we're going to calculate f1 checkout, and in the same way you can calculate recall, precision and every other thing which you want. But here we have two main matrix, f1 and iou. So we have this an empty and not an empty, a list which contain class f1 and iou. We print it because I also want to print the result on screen also and save it in the file. So we iterate over the score. Okay, first let me give you the shape of this score, but it would take time now for this to get complete. So what I'll do, okay, should be test x, test y. Yeah, just to check, we'll limit it to 10 classes. So you can see this is how it work, and you can see the shape 2 by 3. 2 by 3 refers to 2 refer to, because we have 2 matrix, and 3 refer to class. So here what we do, we iterate over this score dot shape 1 all the three class. So we have the class, what specific class we print it, then we have f1 score, then we have checkout score, then we have these proper lines, these things, so that they print properly. Okay, we write it inside this file, then we print them, all sort of thing. Then after that, here we have this mean fps, and before that we have, what do we call this, the mean. So here we have result for individual class, background v1 v2, but this mean result is calculated over the v1 and v2. In the mean result I don't include the background, because for us as a researcher, background is not important. The importance is two class, v1 and v2. So mean should over be both the classes, not over the background. Maybe you want to include background, you can make appropriate changes. So now I'll remove these 10 samples and I can replace the weight file. Merge. Let's skip this score.csv. I think I've trained it for about, I think 40-50 epoch, I don't even remember that now. Let's run this and see how well it performs. It's gonna take a bit of mint, but that's not an issue. So I hope you learn something from this video, and maybe it would help you with your projects, assignment or research paper also. because even I'm a researcher and I used to write research paper, but now I'm down. I need to update myself with the latest large language model, language vision model, transformer, all sort of thing. So I'll update slowly. Even I don't want to left behind. So I would say study those also. Those are also helpful because you need to keep yourself updated with the latest research if which is happening in the community. Because latest thing is important, because nowadays I see everyone is using transformer, large language model, chat gpt, question answer thing, even in segmentation task. Okay, now result has come. So background f1 is 97%, v1 is 59, v2 is 41. So result is fine and mean is 50. So mean score is fine and fps is 143.95. So frame per second is also good. This can also improve because for now we give only one image in a batch. So if we provide like a batch of maybe 20 images or 30 images, maybe it can support 30 to I think 40, because image size is 256 by 256. And also one more thing, because now we are testing, not training, so gpu memory, we have much larger gpu memory available. Now let me show you this core file. So you can see a nice way to save your result in this csv file. Save it and let me show you the results. I'll upload the code, you can check it from there. Now you can see the results are good and they are matching. So now here you can see it's working fine with both the classes. One class is the greener one is big blob type structure, second BD is like leafy tiny structure, so it worked with both. Yeah, here we have some under segmentation, and I think the ground truth is not good because you can see in leaf is there, so that's why we can say the prediction is good in comparison to ground truth. So these things happen while annotating data because it takes time, so people often do these small tiny errors, and these are maybe good for your model also because this shows the real performance of your model. So I hope you learned something from this video, and if you really learned something and enjoyed it, please make sure to like the video, share it with your friend or on your social media, and do subscribe the channel for more such video. And maybe in future I'll start working on the object detection also. Okay, so do subscribe to the channel for more videos. Thank you, have a nice day.